So in this video, we're going to prove the average value of f on AB is equal to the integral from a to b of f of x dx times the reciprocal of b minus a. And then we're going to work an example showing how to find the average value of a function over some particular interval. All right. So the theory, then the practice. So with this particular one, the proof, we start by a partition of the interval a to b. So I'm going to start at x1, and pick at x2, x3, x4, all the way out, dot, 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 until I get to my xn plus 1, which I call b here. And then I'm going to pick a ci in the ith interval between x sub 1 and x sub m, or I plus 1. So to give you a picture of what this actually looks like, so say I have some interval, right? So here's my first a, and here's my last b. So I want to find the average value of the function. Maybe the average value is like right here. This is like the average value. Okay, so that's that average output there. Now, how I cut this interval up to figure out what numbers to use for the average, what I do is I start at a equal to x1, so that'd be the first input I make, so that gets me an f of x1, right? And then I'll go to x2, and that gets me an f of x2. And then I'll go to x3, so that gives me an f of x3. And then I'll just do this infinitely many times till I get to some random arbitrary xi. And then the next one after xi, just like the next one after x2 was x3, I just add 1 to the I, so I plus 1. So what I'm focusing on, people, is this interval right here between xi and xi plus 1. That's what this represents. I want to find some ci, okay, some ci in between there. Now, I don't care where that ci is located as long as that ci is doing its job, right? It's between xi and xi plus 1. Okay, so it's just some random ci in there, in that ith interval. And whenever I plug that in, I get f of ci, okay? So what I want to do is I want to average this out. So let me erase this real quick. Takes me a little bit of time, but we'll get it done here in just a second, people. So I want to average C1, C2, C3, all the way out to Cn, okay? So if there's x sub n plus 1 cuts in my graph, then I have n subintervals that the whole thing is cut up into from a to b. There's n subintervals. So I start at f of c1 and I go all the way out to f of cn. So there's n values that I'm trying to average. So if I'm trying to average n items, how do I average numbers? Well, I add up all of the numbers. So fc1 plus fc2 all the way out to fcn. And then I divide by the total number of them that I added up. Well, there were n total there. So the average value of f on AB is this right here. That is that finite value there with n subintervals. But since we made it arbitrary, we're going to be able to take the limit as n goes to infinity and figure it out. We'll save that for the end. So let's rewrite this in a more sophisticated way. Instead of writing plus, 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 we have a symbol called summation, right? The sum. That's a better way than writing plus, 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 right? So I start at a I equal to 1. That's why I started here. And then I go up to 2, 3, 4, 5, 6, 7, 8, blah, 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 all the way to n. So I sum up to n. And what am I summing? I'm summing my f's of ci. Okay? So I've got this right here. Now, what I can do here, instead of having sum all these and divide by n, that would be the same thing as saying f of c1 divided by n plus f of c2 divided by n plus f of c3 divided by n, and so on, right? I can divide by n in each individual term. So I'm going to pull that n to the inside of my sum, and I can do that since it's not dependent on the index I. Okay? So I pull this 1 over n factor inside of my sum here. And now I'm going to multiply by a clever 1. But if I multiply by b minus a, I need to divide by b minus a. That way I am multiplying by this clever 1 that doesn't change the original equal sign that we have here. Okay? Now, why in the world did I do this? Well, maybe you might be seeing this, but what's happening here is now I have a b minus a here divided by n, which is a special thing that we'll talk about in just a second. And so I keep the b minus a in here, but what do I have to do? I need to move the b minus a in the denominator outside. So I'm going to move that one outside. And so what do I know? What's special about this right here? Well, b minus a divided by n, this would be, if I had an equally spaced partition, would give me delta x. Okay? Remember, if I have interval from a to b, to find the length from a to b, I do b minus a, right? And if there's n sub-intervals, then if I divide by n, that gets me the length of one of those intervals, and we call that width there, okay, delta x. All right, so that's that definition we learned in a previous video. All right, so pretty clever trick there. Multiplying by 1, really being a good mathematician is about knowing how to multiply by a clever 1 and knowing how to add a clever 0. Okay, which you saw whenever we were taking, like, figuring out deriving derivatives of like sine using the definition of the derivative. Okay, so what do I have here? So I've got 1 over b minus a times f of times the sum from 1 to n of f of ci right there, multiplied by delta x. So that's my delta x right there. Now what I'm going to do is I'm going to let n go to infinity. So instead of summing up n a finite number of rectangles, I'm going to sum up infinitely many number of rectangles. And as I do that, my delta x, my width gets smaller and smaller. Remember, delta x is defined to be b minus a over n. So the limit as n goes to infinity of b minus a over n happens to be approaching 0. So the widths are going to 0, but your number of rectangles is going to infinity. So you've got this battle between 0 and infinity going on here that actually produces this finite number for you. Pretty cool stuff. So whenever I do this, I take the limit as n goes to infinity. And so the only thing that the limit affects is this n right here. It pushes it to infinity. And whenever we do this, we get this to be a Riemann sum, okay? A constant right here multiplied by the definite integral from a to b f of x dx. So what have I done here? I have proved that the average value of f on AB is equal to 1 over b minus a times the definite integral from a to b f of x dx, which is exactly what I wanted to prove here. Pretty cool stuff. So let's now use the practice, and no longer the theory, but the application. Find the average value of the cosine function from pi over 2 to pi, okay? So the average value of f on pi over 2 to pi. So a is pi over 2 and b is pi. this is equal to 1 over b minus a, integral a to b f of x dx. Well, my f of x here happens to be cosine x. And my b minus a, well, my b is pi and my a is pi over 2. So I have pi minus pi over 2, integral from a to b, so that's pi over 2 to pi. So now all I have to do to calculate the average value is to figure out what that is and then multiply it by the definite integral. So it's a number, it's an average value. So I integrate cosine. The integral of cosine is sine. If I simplify this, I get that pi minus pi over 2 is pi over 2, so 1 over pi over 2 equals the sine of x, integral of cosine is sine, evaluated from pi over 2 to pi, okay? So if I keep change flip, just to show you, 1 and then change from division to multiplication and then flip, that's 2 over pi. So that's where that 2 over pi comes into play with that constant in front there. Okay, and then I'm integrating sine f of b minus f of a. So sine of pi minus sine of pi over 2. And so what does this get me? Well, if I think about a unit circle, sine of pi, the y value over here is 0. The y value at pi over 2 is actually 1, so I have 0 minus 1. So I have negative 1 times 2 over pi. Negative 1 times 2 over pi is negative 2 over pi. Okay? So hopefully this video was helpful for you. If you want to see a picture of this, maybe you're asked to draw a picture of this on an exam or something, what I would do is I would, well, let me see if I can figure this out. Let's add in a sticky note. How about that? Okay, let's make it a little bit narrower. Yeah, that'll work. All right, so I'm going from so cosine, I guess we can start that. So 1, 2, 3, 4, 1, 2, 3, 4. So it's going to go down, and then, I'm sorry, let's try this. So it's going to go down. So that's over 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Like this, okay? So this would be 0. This point here would be pi over 2. And then this point here would be pi. So down here would be negative 1. Up here would be 1. And what I want to do is I want to find the average value from pi over 2 to pi, okay? And so what I found, all right, so that area there is this negative area right here, all right? So that's the integral. This here represents hold up, let's see here. So let me do this. So this number represents the average value, right? So 2 divided by pi, what is 2 divided by pi? So 2 divided by pi, let's see, where is my pi button? Okay, right there. That's 0.636. So 0.636 is somewhere in here. So somewhere in here. So this value right here, this is my negative 2 over pi value here, okay? So this area, this red area right here, is equal to that orange area of the function cosine integrated at that point. All right, so kind of an interesting thing going on there. All right, so the average value of the cosine function on that interval, the average value of f of x equal cosine x on the interval, closed interval from pi over 2 to pi, is -2 over pi. So kind of cool that you can find the average value given a infinite amount of inputs that you could plug in and then average together. Remember, I'm plugging in infinitely many points I could plug into this graph and then take them and then average them all up to get some set average. Now don't worry too much about that x bar. If you took statistics, you know x bar is just a fancy way to say average.